Hello friends, in the previous lecture we looked into one way of describing expression that forms the building block of tensorial notations. Now the last two lectures might be or would have been a bit heavy. The reason is because we are venturing into a new way of or a new mathematical technique that is hugely relevant to our research in materials. So since this provides us a way into a different numerical technique apart from the partial derivatives or the ordinary derivatives, the calculus that we are familiar with, the path towards this new technique is quite rather it's not that straightforward, and that's the reason the last two lectures have been a bit heavy. And as mentioned earlier, we saw a way of rather expressing a set of equations, set of relation in a simpler manner using index. Now this rather forms the basis, or this forms the foundation of the tensorial notation. Now all these discussions, the last two discussions particularly wherein we were attempting to introduce this index and through the index into the tensorial notation or tensor notations, these started with coordinate system and the coordinate system which are inverse of each other. So for that we consider generic coordinate systems like Z1, Z2 and Z3. Another set of coordinate systems that is Z1 prime, Z2 prime and Z3 prime. The reason we conventionally the prime is used because this allows us to stick with the variables that we have considered, the notations that we have considered. So if we consider I, J and K, and if you combine or include prime along with it, so that gives us 6 different notations. If we, instead of using primes, if we use different notations, for instance I, J, K, L, M, N, and at some point we will run out of alphabets. So therefore this prime, even though it is a bit confusing, the prime is rather preferred over changing the notations. So now we have considered two coordinate systems, Z1, Z2 and Z3, Z1 prime, Z2 prime and Z3 prime, and these we assume are inverse of each other. So it means when I express Z1 as a function of Z1 prime, Z2 prime, Z1 prime, Z2 prime, and as a function of Z3 prime, and this Z1 prime, Z2 prime and Z3 prime, if I consider this subsequently as a function of Z1, Z2 and Z3 in the same way Z2 prime as the function of Z1, Z2 and Z3 in the same way Z3 prime as a function of Z1, Z2 and Z3, I will be able to recover Z1 not as a function but as an independent variable. So we are considering two different coordinate systems, and when I consider one of the coordinate as a function of another coordinate system, and each of these other coordinate systems is subsequently considered as the function of the original coordinate system, then I'll be able to recover the corresponding independent variable. Now this expression can also be written down for Z2, the coordinate of the initial coordinate system, that is the original coordinate system. So Z2 can be written as a function of Z1 prime, Z2 prime and Z3 prime, and this subsequently Z1 prime as a function of Z1, Z2 and Z3, Z2 prime as a function of Z1, Z2 and Z3, Z3 prime as a function of Z1, Z2 and Z3. This will yield me the corresponding independent variable Z2. The same can be expressed for Z3 as a function of Z1 prime, which is subsequently a function of Z, Z2 prime, which is subsequently a function of Z1, Z2 and Z3, Z3 prime, which is subsequently a function of Z1, Z2 and Z3. Z will lead me to the corresponding independent variable, that is Z3. Now the reverse of the same relation can be considered, wherein we are considering the function. We are treating Z1 prime as a function of Z1, Z2 and Z3, and each Z1, Z2, Z3 we are subsequently treating them as a function of the prime coordinates, that is Z1 prime, Z2 prime, Z3 prime. The same way Z1 prime, Z2 prime, Z3 prime, the Z3 as a function of Z1 prime, Z2 prime and Z3 prime. This will yield me or this will yield the corresponding independent variable, that is z1 prime. Now the same operation or same expression can be extended to the other coordinates of the prime coordinate system, that is z2 prime, which is expressed as a function of z1, which is subsequently a function of the prime coordinate system, z2 function of the prime coordinate system, and z3 function of the prime coordinate system, and ultimately you will end up with the corresponding independent variable of z2 prime. The same can be extended to z3 prime, function of z1, z2 and z3, which is subsequently the functions, and ultimately this will yield me the corresponding independent variable z3 prime. So what essentially we have is, we have considered the inverse relation between the two coordinate systems of three axes. It is expressed by using 6 different expressions. So two coordinate system inverse of one another. In order to show that these two coordinate systems are inverse of one another, we need 6 different expressions. Now, in our previous lecture, we saw that using index, it is possible for us to write the index that is associated with tensor notation. It is possible for us to write the first 3. This expression, and this expression in using a single relation. So that single relation will be of this form, Zi. We are talking about the 1, 2, 3 prime coordinate system, 1, 2, 3 coordinate system, Z1, Z2 and Z3 coordinate system. So this is expressed as a function of the prime coordinate system, and the prime coordinate system is subsequently the function of the Zi coordinate system, and this will yield me the corresponding independent variable. So what essentially we have done is, all these 3, the ones highlighted in red, all these 3 different expressions, we have simplified it, and using the index high, we have written it down using a single relation. The single relation encompasses all these 3 different expressions that talks about the inverse relation. Now this Z prime here, it's essentially Zi prime, but since it is within the bracket, it is treated as a variable. Of course it's a function, but it is treated as within the bracket. So conventionally we can get rid of the I here, and therefore it is represented as Z prime. And in the same way, this is Zi, and since it is also considered as a variable within the bracket, we are treating it as, we are just mentioning Z. So therefore the 3 expression can be rather summarized or expressed shortly in this manner. So using the index that is associated with vector notation, it is possible for us to express all these 3 different expressions in a simplistic manner. The reason we need to understand this expression is because whenever we are dealing, particularly in the materials research, when we are dealing with plasticity and elasticity, we will see expressions such as this, and only when we are able to understand what this means, only when we are able to understand what these usage of this index is, then we will be able to decipher, we will be able to make sense of those expressions that we often come across when we are dealing with elastic behavior or the mechanical behavior of a material as a whole. Now, similar to the expression highlighted in red, the expressions in blue, so these 3 expressions that start with the prime coordinates can be expressed as Zi prime, which is a function of Z, which is subsequently a function of the prime coordinates, and ultimately this yields me, or this leads me to the corresponding independent variable. So this expression here, it encompasses, or it includes 3 different expressions that starts off with the prime coordinate, and this prime coordinate is expressed as a function of a function, and it ultimately leads to the corresponding independent coordinate. So we have reduced 6 different expressions to 2 distinct relations using index. Now we also saw in our previous lecture that each of these expression, based on each of this expression, it is possible for us to find the corresponding partial derivative. So let us start with this expression here. This expression, from this expression, it is possible for me to estimate the partial derivative of Z1 prime, which is a function of a function. So a function of a function can be expressed in this manner. So Z1 prime, the partial derivative of Z1 prime, which is a function of a function with respect to the corresponding independent variable Z1 prime, which is in the right hand side of the expression. Now this partial derivative can be expressed as, this partial derivative can be written as z1 prime with respect to z1. So what we are doing is we are extending the chain rule here, plus rather z1 prime with respect to z2 and the z2 with respect to z1 prime. The same way, so z2 is a function of z1 prime, 2 prime and 3 prime, and therefore we are considering the partial derivative of z2 with respect to z1 prime. In the same way, z1 prime with respect to z3 and z3 with respect to z1 prime. Now this, when you consider, so this is the partial derivative starting off with this expression here. So this, from this we have ended up here, and so this expression, this extended form of, or the chain rule which is being used, it is for the left hand side of the expression, and the right hand side we end up with 1. Now the same way, it is also possible for us to estimate the partial derivative of z1 prime, the function of a function, with respect to z2 prime. So we are considering the partial derivative of z1 prime, which is a function of a function, with respect to z2 prime. So the corresponding expression would be tau z1 prime with respect to z1 and tau z1 with respect to tau z2 prime. So this expression is extended in this way, tau z2 prime. All that we are doing is we are replacing this particular term with tau z2 prime 3 with respect to tau z2 prime. And this, what will happen is, so from this expression alone, from this expression, from this relation, that is z1 prime as a function of a function which leads to its corresponding independent variable of z1 prime, we have arrived at one expression, and from the same relation, the one highlighted in blue, this expression, we are now expressing another partial derivative, and this partial derivative will be equal to 0 because we are considering the partial derivative of z1 prime with respect to z2 prime at the right hand side of the expression. So this will turn to be 0. Now correspondingly, from the same expression, we will be able to show that the partial derivative of z1 prime as a function of a function with respect to z3 prime will be 0. So we have one relation, and from that one relation we are able to extract 3 partial derivatives, partial derivative of a function with respect to the corresponding independent variable, and that will yield us either, in this case, the first case it led us to the value of 1, the second case 0, and in the third case 0. In the same way, it is also, so all these stems from the first relation. In the same way, it is also possible for us to express the partial derivative of the second coordinate system, tau z2 prime, which is expressed as a function of a function, with respect to the corresponding coordinates, that is tau z1 prime. Now this stems from the second expression here. So the term that is being written down here, so this term, it stems from the second relation here. So we are considering the partial derivative of this coordinate with respect to a corresponding coordinate, that is z1 prime. So when you extend the partial derivative in this form by considering the chain rule, this will turn out to be 0. In the same way, when you consider the partial derivative of z2 prime, again treating as a function of a function with respect to z2 prime, this will be 1. However, the partial derivative of z2 prime, treating it as a function of a function with respect to z3 prime, this will turn out to be 0. And in the same way, it is possible for us to arrive at similar partial derivatives from this relation here, from this relation here. It is possible for us to arrive at another three partial derivatives, that is tau z3 prime with respect to tau z1 prime, which will turn out to be 0, because again the 0 comes from the right hand side of the expression, we are considering the partial derivative of this variable with respect to another variable. This is an independent variable with respect to another variable, which is again an independent variable, so therefore it turns out to be 0. And again, it is possible for us to consider the partial derivative of this as a function of a function with respect to z2 prime, it will be 0. And finally, as a function of a function with respect to z3 prime, this will turn out to be 1. So what essentially we have done is, we have seen in order to express the inverse relation, we need inverse relation between two coordinate system. We need 6 different expressions. That is what we saw earlier. The ones highlighted in red, they contribute to 3 relations, and the one highlighted in blue, they contribute to 3 other relations. So what essentially we have is, we have 6 different expressions that help us express the inverse relationship between the two coordinate system. These 6 expressions can be reduced to 2 different expressions using the index I and I prime. Now from these 6, so when you consider just 3 of this expression here, when you consider just this 3 highlighted in blue, from this 3 we are able to estimate 1, 2, 3, 4, 5, 6, 7, 8, 9 partial derivatives. From these 3 expressions here, we are able to estimate 9 different partial derivatives. Now let us see if it is possible for us to express the partial derivatives using the index that we have introduced earlier. So if you look closely, now what we have is the index of these variables. So index of these terms here, they remain the same. The bottom and the top, they remain the same, and all that they indicate of is the summation. So what essentially we have is, we can introduce here the Einstein summation convention, and the ones at, so this bottom and top, the index at the bottom and the top, they are identical and they indicate summation. However, the index at the top and bottom, they are distinct and they pertain to a specific expression. They do not vary for a specific expression. So these indices, the ones highlighted in red, they are characteristic feature of this specific expression here. They are constant for a specific partial derivative. So this we observe in this expression as well, and they have a characteristic notation in this expression as well. So while these bottom and top indices, they are identical and they represent summation in a given expression, the top and bottom indices, they play a different role. They are a characteristic representation of a given expression, and therefore we differentiate the top and bottom indices differentiate top and bottom indices from the bottom and top. The top and bottom indices, the one in red, we refer to it as the free indices or free index. The bottom and top that indicates the summation, we refer to it as the dummy index. Again, this is something that we have already seen. So now that we have differentiated the top and bottom and top index, it is possible for us to represent these sets of 9 different partial derivatives using a single expression. Earlier we simplified 3 expressions using one relation that involves index. Here what we are doing is, we are trying to express 9 different partial derivatives using index and represent it in the form of a single expression. Now in order to do that, we have to introduce the appropriate index. What we essentially have in this case is the index that are rather dummy index that indicates the summation. So these dummy indices 1, 2 and 3, they can be replaced by I. So 1, 2 and 3. So we are trying to now express all these 9 PDEs using a single expression. So we have Z that remains the same, and the difference is brought about by the index. Now in the top and bottom, so in the top and bottom, the index that indicate the summation, irrespective of the what we consider which coordinates we start off with, irrespective of which coordinates we start off with. If we start with Z1 prime, Z2 prime or Z3 prime, the dummy index, the index at the bottom and the top, again the order is important, the index that is at the bottom and the top, it remains the same. We can start with z1 prime, it remains the same. We can start with z2 prime, it remains the same. We can start with z3 prime, it remains the same. And that's the reason why we refer to it as the dummy index, and all that it indicates is the summation. So therefore, this can be represented by I prime, or rather I and I. Okay. The reason we refer to this as I is because the dummy indices are of the value 1, 2 and 3. It's not 1 prime, 2 prime and 3 prime, it's just 1, 2 and 3, and therefore the dummy indices are represented by I here. Now, when you consider the free index of the free indices, the other indices that has been highlighted in red, the index that is highlighted in red, these vary with the coordinate we consider. If we consider the z1 prime coordinate with respect to z1 prime coordinate, then this index, that is the highlighted, the free index, they are identical. However, if you consider z1 prime coordinate with respect to z2 prime coordinate, these indices, they vary, they are unequal. So initially when you consider z1 prime coordinate with respect to the z1 prime coordinate, the indices, they are identical. When you consider the other cases, they are not identical. So in this case they are not identical, in this case they are not identical. The same way in this case as well. When you start off with the coordinate z2 prime and you differentiate it with respect to z1 prime, in this case the free indices, they are not identical. So therefore we need two different indices to represent the free indices. Again, unlike the dummy indices, which are for a given term identical, they assume the same value at the bottom and at the top. The other indices, the one that assumes top and the bottom, they are not, they can be identical and they cannot be identical. There is the possibility of them being identical and non-identical depending on which partial derivative we are considering. So the nature of these free indices depends on the partial derivative that we are considering. So they can be identical or they cannot be identical. So therefore we need to have a different representation for these indices that are free indices, that are not dummy indices. So therefore we represent it by I prime and j prime. So we have I prime and we have j prime. Now again we are considering the prime along with it is because we are the dummy indices, while they are 1, 2 and 3, in case of the free indices they are 1 prime, 2 prime and 3 prime, and depending on the value of this prime indices we need to have the appropriate PDEs. While the dummy indices, they are just there, for a given term they will be identical, and they are indicating the summation. The free indices, the I prime and the j prime, depending on the value they assume, they indicate an entirely different PDE. So therefore we have I prime and j prime. So it is possible that I prime can be equal to j prime or I prime cannot be equal to j prime. So what essentially we have done is we have represented the 9 different PDEs using a single expression here, and this single expression, it includes both dummy and free variables or the free indices. So these are the free indices and the dummy indices are high. So this I can be 1, 2 and 3, and under, so again it is important for us to mention that under Einstein's convention, this is nothing but the summation with respect to I. And again, for each value of I prime and j prime, we are talking about a separate PDE. Now in the same way, like here, it is possible for us, so when you consider the set of these 3 expressions, so when you consider the set of these 3 expressions, that is starting with z1 expressed as a function of a function that leads to z1 variable, z2 expressed as a function of a function that leads to a z2 independent variable, z3 expressed as a function of a function leading to a z3 variable. From these 3 we will be able to again generate 9 other PDEs. So from these 3, 9 other PDEs can be generated. And these PDEs, without getting into the total expression, these PDEs will be of this form, that is dou z1 by dou z1 with respect to the partial derivative of z1 with respect to z2, the partial derivative of z1 with respect to z3. Now we will consider the partial derivative of z2 with respect to z1 z2 with respect to z2, z2 with respect to z3. The same way we can start off with the coordinate z3 and its partial derivative with respect to z1, the coordinate system z3, its partial derivative with respect to z2, the coordinate system z3, its partial derivative with respect to z2, and z3. Now we have already seen the expression, so we have the expression, and when you estimate the partial derivative, this will turn to be 1, this will turn to be 0, this will turn to be 0. The same way, this will turn to be 0, this will turn to be 1, and this will turn to be 0, this will turn to be 0, 0 and 1. So the values of this derivative can be estimated from this expression here. So in previous case, we started off with the prime coordinate system and the corresponding derivative. It gave us 9 PDEs. Now we started off with the 1, 2, 3 coordinate system, I coordinate system, and from that we have arrived at 9 different PDEs, and we were able to calculate the corresponding values from this relation here. Now it is possible for us to write this derivatives, write these 9 PDEs using a single expression of this form here. So if you consider, for instance, let us consider the partial derivative of z1 as a function of a function with respect to z2. So this will be of the form z1 partial derivative of z1 prime, the partial derivative of z1 prime with respect to z2. In the same way, z1 partial derivative of z2 prime, partial derivative of z2 prime with respect to z2. Same way, we will consider the z3 prime and z2. So again, here in this case, the dummy variables are I prime variables and the free variables are I. So this distinction we need to make. The dummy variables, or these are the free variables, they are I, and the dummy variables are the I prime variables. And again, the indices of the free variables, they can be equal or they can be non-identical, as we see in this case. If you consider this PDE here, in this case the free indices will be identical. In this case they are non-identical. Therefore our representation of the 9 other PDEs, so the 9 other PDEs would be of this form, wherein the partial derivative of zi with respect to the dummy variable, and again with respect to the dummy variable, and set j. The reason we have j here, because the free variable, they can be identical or they cannot be identical. Now what we have done is, we have now represented close to 80 different PDEs using set of two relations, 18 different PDEs using two relation. Now if you look closely, let us focus on this page here alone. If you look closely, in this case, so each of these 1, 2, 3, so each of these are a PDE. They can be extended using a chain rule. Now when you look closely, so this is the expansion, the chain rule expansion for each of this PDE is represented using the tensor notation in this manner. Now if you compare this notation with respect to this expression here, this tensor notation with respect to this notation here, we will notice that when the values assumed by the free index are identical, when the values assumed by the free indices are identical, then the corresponding partial derivative will be 1. When I, so we have two free indices here, that is I and j. When I is equal to j, then this PDE here, it will yield 1. When I is not equal to j, this PDE will yield 0. So this PDE is this representation of 9 different PDEs. So what we have done is, we have two expressions. That is, we start off with the prime coordinates I prime and differentiate it with respect to the other coordinate, and this will yield us 9 different PDEs, and this is encompassed in this form here. And when you start off with the other coordinates of zi and take its derivative with respect to the or by including the prime coordinates. So you will end up with an expression of this sort here. So essentially what we have is this expression. It indicates, or it encompasses, it includes 9 different PDEs, this 9 other PDEs. Now, irrespective of the indications of these PDEs, irrespective of what PDEs these two relations encompass, when in both these cases, these two represent the free indices, and when the free indices are identical, the value of this PDE will be equal to 1, and if the free indices are not equal, then the value of the PDE is 0. So again, the PDE will change. We need a characteristic PDE for a given combination of the free indices. When the free indices are identical, then the value of the PDE is 1. When the free indices are not identical, then the value of PDE is 0. So it means this as a conditional equivalency, meaning this PDE will be equal to 1 when I prime is equal to j prime, and 0 when I prime is not equal to j prime. And this PDE will be equal to 1 when I is equal to j, and 0 when I is not equal to j. Now, such expression, such relation can be simplistically expressed in this manner as delta I j, or I prime j prime. So delta I prime j prime. So this delta here, it means that when I prime and j prime are equal, they assume a value of 1. When I prime and j prime are not equal, they assume a value of 0. The same way, this here can be expressed as I and j, and when I and j are equal, this value, the delta, would be 1. When I and j are not equal, the corresponding value of the delta would be 0. This is what is often referred to as the Kronecker delta. So the Kronecker delta is rather a simplistic representation of this condition here. So we have a condition, and that condition states that when the free indices are identical, then the value of the PDE is 1. The free indices, so you have an expression, and that expression involves involves free and dummy indices. And when the free indices are identical, then the value of that expression turns to be 1. So in this case, we have a PDE, so it can be any expression. So you have an expression that involves, that you have written it down using free and dummy indices. Now, when the free indices are identical, the value of this expression turns out to be 1. When the free indices are not identical, the value of this expression turns out to be 0. So this can easily be represented by this term here, this delta term here, and this is what we refer to as the Kronecker delta. So what Kronecker delta essentially means is, so in this Kronecker delta, when you consider the way we have represented it, it includes just the free indices alone, I and j, and when I and j are equal, then the corresponding value, the value of the Kronecker delta will be 1. If they are not equal, it turns out to be 0. So this equivalence, this relation is rather easily represented by the Kronecker delta. In the first term, the Kronecker delta has the indices of I prime and j prime, because those are the free indices here. The second expression, it has I and j, so those are the corresponding free indices. Now again, what essentially we have done is, instead of having the indices at the bottom or at the top alone, in all these representation, we have the indices at the top alone. So if you consider this PDE, and each PDE, we have 9 PDEs, and each PDE has a corresponding term, a numerator and the denominator, and in both numerator and denominator we have an index associated with it, and all these indices are rather present at the top of each of these terms. But now what we have done is, we have introduced a Kronecker delta, a term for a simplistic representation of this expression, and here we have indices that occupy both top and the bottom. So this is, we are moving from a single index representation of a term to a representation of a term that requires 2 indices. So this term here, just this term here, it requires 2 indices. So one at the top and one at the bottom. So let us try to understand, is there any significance to the order, the one at the top and one at the bottom. So in this case, there appears to be not much significance, because it just states that the Kronecker delta just states that when the indices are identical, the value is 1. If they are not identical, then the value is 0. But this is for a special case. Let us see if there is any significance associated with this I and j. Now, the place we have introduced this Conical delta is when we are considering the PDEs, or the partial derivative of a coordinate system with respect to its corresponding coordinate through a different coordinate system. We started off with a prime coordinate system, and we are finding out the partial derivative of this prime coordinate system with respect to its prime coordinates through the other coordinates, that is I, j and k, through the non-prime, that is I, j and k coordinate. Now, when you consider rather the representation, when you consider rather another way of describing these partial derivatives, so it is these 9 partial derivatives that are expressed as the Kronecker delta. It is these 9 partial derivatives that are expressed as, so these 9 partial derivatives have been expressed rather using this simplified notation, and this is what helped us look into, or rather invoke, the Kronecker delta. So what essentially we have is, we have 9 PDEs, and that 9 PDEs we have represented it using a single expression, and then that single expression we related it to Kronecker delta. Now let us go back to our consideration of this 9 PDE, and it is possible for us to represent this 9 PDE into or as a matrix. We can represent this 9 PDEs as a matrix, and that would give us the Jacobian. So we can represent these 9 PDEs in a matrix form, and that would give us the Jacobian. And when you consider the Jacobian of this 9 PDEs, it will be 1 partial derivative of z1 with respect to z1, the partial derivative of z1 with respect to z2, the partial derivative of z1 with respect to z3. In the same way, the partial derivative of z2 with respect to z1, the partial derivative of z2 with respect to z2, the partial derivative of z2 with respect to z3. So this is, I'm just writing down the Jacobian of this function of the 9 PDs. So now we have a 9 PDs, and I'm writing it down as a matrix with respect to z1, 3 with respect to z2, the partial derivative of z3 with respect to z3. So what essentially we have done is, the 9 PDEs we have expressed it in the form of matrix. Now we also have, so these are the 9 PDEs, we have expressed it in the form of matrix, and there are corresponding values that we have identified for each of these PDEs, and if we mention, so this first term will be 1, and the second term, the next term will be 0, and the third term will be 0. The other term, this term would be, that is the term in the second row first column would be 0, the second row second column would be 1, 0. So what we will end up having is, we'll end up having the identity matrix. So what essentially we have is, this expression here is written down in the form of a matrix. So this expression here, it encompasses 9 PDEs, and all these 9 PDEs, they are written down in the form of a matrix, and that matrix is a unit matrix, and essentially what this matrix indicates is the same as what the Kronecker delta indicates. Essentially it is a unit matrix, and it means when the I and j values are equal. So when the row and column, when you assign a values to the row and column, when the row and columns are identical, the value assigned to the rows and columns are identical, then the value is 1, if not, the value is 0. So it has the same rather expression, or same rather description similar to that of the Kronecker delta. So this is nothing but the Kronecker delta expressed in the form of a matrix. So what we have done is, we have expressed the 9 PDEs into a single expression, and we have related the single expression as to the Kronecker delta. Now this 9 PDE, we have written it down in the form of a matrix, and this matrix, it leads us to an identity matrix, and this identity matrix, if you compare this identity matrix to that of the Kronecker delta, it is nothing but the identity matrix in itself is a representation of the Kronecker delta, meaning in this case the I is equal to j is equal to 1. Here the I is equal to j is equal to 2. here the I is equal to j is equal to 3. So when you consider the matrix, the value of 1 is when I is equal to j, and here 1 is I is equal to j and that is equal to 1. Here I is equal to j. So when you consider the matrix representation, this term here is I is equal to j is equal to 2 and I is equal to j and is equal to 3. So this here is the matrix representation of the Kronecker delta. So what essentially it means is this Conical delta, the I here, it indicates the row of your matrix, whereas the j here, it indicates the column of your matrix. So this matrix, in this matrix, so when you have the Conical delta and then translate it into a matrix, you will end up having such a matrix. So we are relating the Conical delta to that of the identity matrix because both come from the same set of PDEs. So this PDE and this are both the same. This is one way of representing the PDE and this is another way of representing the PDEs. So this is one way, this is another way, and the one way it yields us the Kronecker delta and the other way it yields us the identity matrix, and therefore we are relating the identity matrix and the Kronecker delta. So again, this expression here and this expression here, they consider both these consider set of 9 PDEs. So both these consider set of 9 PDEs, and one it yields Kronecker delta, the other it yields identity matrix. So therefore we are relating these two, and when we relate these two, we find that the I here, it represents the row of our matrix, whereas the j, it represents the column of your matrix. So therefore when I here, so this one, when I is equal to j is equal to 1, you have 1 when I is not equal to j. So this will be I assuming the value of 1 and the j assuming the value of 2. The same can be seen here. So the ones at the top, they assume the same value. So ones at the top, so these indices, they assume the same value, and the ones at the bottom, they vary. So it means at the top, the I, or rather the I here, it indicates the row, whereas at the bottom it indicates the column. So the Kronecker delta, we have, so one characteristic feature, one unique feature of the Kronecker delta is it is expressed using two indices. A single term is expressed using two indices. So it means this term can be expressed as a matrix. Again, usually we have a term that is expressed using a single index. Now we have Kronecker delta that is expressed using two indices, and when you look closely, the top index of the Kronecker delta, it indicates the row, and the bottom index of the Kronecker delta, it indicates the column. So j here, it indicates the column. So along the row, the j varies, and along the column, it's the I that varies. So the I, it indicates the row that is highlighted in red. So the top index, it indicates the row, whereas the bottom index, it indicates the column. So that is what we observe here. When you move along the row, the top index, it remains the same. You are moving along the row, the top index, it remains the same. When you are moving along the column, the bottom index, it remains the same. So whenever we see a variable, whenever we see a term that involves or that is expressed using two indices, conventionally the first index, it indicates the, so that particular term can be expressed in the form of a matrix. So what it essentially means is the Kronecker delta, the uniqueness about the Kronecker delta, it requires two indices. So this means this can be expressed in the form of matrix. So this term can be expressed in the form of a matrix, and this matrix is of the size I cross j, and the I, it indicates the row, and the j, it indicates the column. Okay. So essentially what we have seen is, we have introduced what a Kronecker delta is, and the Kronecker delta, it captures the 9 different PDEs, the values assumed by 9 different PDEs. Now the Kronecker delta, it requires two indices to represent, to describe it, and therefore this is different from all the other terms that we have considered thus far, which requires only one index. Now when you have a parameter that requires two indices, it means it can be represented in the form of a matrix. And the dimension of the matrix is the product of these two indices. Top index, it represents the row, and the bottom index, it represents the column. Now, this can be extended to, so this conical delta is principally an identity matrix. So it is principally an identity matrix. Supposing if I have a matrix of this sort, a 3 cross 3 matrix of this sort, A, 2, 3. So this is something that we are all familiar with. Just a matrix, a 3 cross 3 matrix. Now this matrix 2 can be represented in or using two indices I and j, where the I here, it indicates rather the row of your matrix, and the j, it indicates the column of your matrix. So there are two ways of looking at it. The entire Kronecker delta can be expressed in the form of a matrix, and that is what we have seen. In the same way, when you have a parameter, a term that requires two index, then it can be represented in the form of a matrix, and each of these terms can be, so you have row that is assigned to the top index and the column that is assigned to the bottom index. So that is the significance of the position of these indices. It cannot be rather reversed. And it is also possible for us to consider, so if I consider a specific value, that is I is equal to j is equal to 1. So in this representation of aij, if I consider a is equal to 1 and j is also equal to 1, then what I am talking about is a specific term a11. Okay, so what we have is, we have seen that when a parameter requires two indices, then it can be represented as a matrix. Now when you assign specific value to these indices, then it translates to a specific element within the matrix. So when you assign I equal to 1 and j equal to I and j both are equal to 1, then it translates to a specific element in this matrix. If I is equal to 1 and j is equal to 2, the corresponding specific element would be a12, and so on and so forth. We will be able to rather represent by corresponding values of I and j, we will be able to represent all the elements of the matrix. So when I have these variables I and j, then the entire parameter can be expressed in the form of a matrix. When I and j assumes a specific value, they represent an element of the matrix. So what essentially we have done is, in this lecture, to bring it all together, we have introduced Conical Delta. The Conical Delta is rather unique because it requires two indices to describe it. It means, so when you have two indices, so that particular variable can be represented in the form of a matrix, and when you assign specific value to the indices I and j, what essentially it will lead up to is the specific elements in that matrix. So with this, we will wind this lecture up, and in the subsequent lecture we will try to understand more about this representation wherein we have more than one index, and how we can perform different operation amongst these parameters that have more than one index. Goodbye.